Hello everyone, and welcome to my course Into the Control Burst. This series is for students, young engineers, and anyone interested in control engineering. My goal is not simply to explain equations or control algorithms. Instead, I'd like to explore the big picture. Why were these control methods developed? What problems are they trying to solve? And what challenges do engineers face in the real world? So before we talk about PID controllers, Kalman filters, MPC, or any advanced topics, let's start with a much simpler question. Why do we need control in the first place? In this chapter, we will cover three things. First, why control exists. Second, what kind of problems control engineers try to solve. And third, how control systems appear in products we use every day. There won't be much mathematics in this chapter. The goal is simply to build intuition. Control systems are everywhere. In the automotive industry, they are used in automatic transmissions, hybrid vehicles, cruise control systems, and many other functions. Aircraft and drones rely on control systems to maintain stability, and robots use control to move accurately. Air conditioning systems use control to maintain comfortable temperature. And active noise control systems use control to reduce unwanted sound. These products look completely different, but surprisingly, many of them are solving the same fundamental problem. So what exactly are we trying to achieve by control? One common objective is stabilization. For example, keeping an aircraft stable during flight. Another objective is tracking. For example, making a vehicle follow a desired speed. We may also want optimization. Maybe we want better fuel economy, higher efficiency, or improved comfort. And finally, we often need disturbance rejection. In other words, we want the system to keep working properly even when conditions change. Okay, so let's look at a simple example. Imagine you are driving on a highway and you want to maintain a constant speed. Everything works fine on a flat road. But then, the vehicle reaches an uphill section. Even though you are pressing the gas pedal by the same amount, the vehicle starts to slow down. So, the environment has changed. The original input is no longer enough, so to maintain the target speed, we need more gas pedal. Then we can keep the target speed. So this is one of the most common control problems you'll encounter. Next, let's look at a completely different system. Suppose you want to keep a room at the same temperature. At first, everything is fine. But then, by the sunlight or something, outdoor temperature rises and the indoor temperature also rises. It gets hot. So we turn on the air conditioning system. Then the air conditioner adjusts its output. It looks like very different product from the vehicle example, but actually solving same kind of problem. Okay, now let's look at what these examples have in common. First, we have a target. Next, we apply an input to the system. The system responds and produces an output. However, disturbances and uncertainties affect the result. As a consequence, the actual output may not match the target. This difference is called an error, and that is exactly why control is needed. The role of control is to reduce the gap between what we want and what we actually get. Now we understand why control is needed. The next question is, how do we reduce that gap? There are two fundamental approaches. The first one is feedback. Feedback reacts after an error appears. The second one is feed-forward. Feed-forward tries to anticipate disturbances and act before the error occurs. These two ideas form the foundation of almost every control system. In the next chapter, we will explore both concepts and see how they are used in practice. Thank you for watching, and I'll see you in next chapter.